The concept of time dilation and the bending of space-time, an exploration of future and past travel. The very notion of time, the relentless, seemingly immutable forward march, has captivated human curiosity since the dawn of recorded thought, yet the edifice of classical Newtonian physics, which once anchored our understanding of time as an absolute, universal constant, began to tremble under the weight of 20th-century scientific revelation, specifically through the twin pillars of Albert Einstein's theories of relativity, which didn't merely adjust our view of the cosmos but fundamentally rewrote the grammar of reality, introducing the astonishing, yet mathematically sound, concept that time is not an independent river but is intimately interwoven with space into a four-dimensional continuum known as space-time, a fabric that can, indeed, be warped, stretched, and potentially traversed in ways that blur the lines between science fiction and observable physics. The core of this radical reinterpretation rests on the principle that the speed of light in a vacuum, denoted by the symbol $C, remains constant for all inertial observers, irrespective of the motion of the light source or the observer, a postulate that necessitated the abandonment of the fixed nature of simultaneity and, consequently, the fixed nature of time itself, leading directly to the phenomenon known as time dilation. Time dilation manifests in two primary forms, each rooted in a different aspect of relativity. Special relativity addresses velocity-induced time dilation, while general relativity accounts for gravitational time dilation. In the context of special relativity, which governs situations where gravity is negligible or constant, the fundamental equation derived from the Lorentz transformations dictates that a clock moving relative to an observer will tick slower than a clock held stationary by that observer, an effect mathematically described by the relationship where the time interval measured by the moving observer, $t, is related to the proper time measured by the clock itself, $t_0, by the factor gamma, which is 1 divided by the square root of 1 minus the ratio of the square of the relative velocity, $v, to the square of the speed of light, $c, squared, meaning $t equals $t_0 divided by the square root of 1 minus $v squared over $c squared. This implies that as the velocity $v approaches $c, the denominator approaches 0, causing the time dilation factor, gamma, to approach infinity, suggesting that time would effectively stop for an object traveling at the speed of light, though reaching $c requires infinite energy for any object with non-zero rest mass, rendering true light speed travel impossible for massive bodies. The reality of this velocity-based time dilation is not merely theoretical conjecture, it is a routinely verified physical phenomenon essential for the functioning of modern technology, most notably the Global Positioning System, or GPS. Satellites orbiting Earth move at approximately 14,000 km per hour relative to ground receivers. According to special relativity, these high velocities cause the clocks on board the satellites to run slower than identical clocks on Earth by about 7 microseconds per day. If this effect were not precisely calculated and compensated for, the positional errors in the GPS network would accumulate at a rate of several kilometers per day, rendering the system useless within minutes. Furthermore, cosmic ray physics provides stunning confirmation. Muons, subatomic particles created when cosmic rays collide with the upper atmosphere, possess an extremely short half-life, often measured in mere microseconds in their own rest frame. Despite this minuscule lifespan, a significant number of muons reach the Earth's surface because, from our perspective, their internal clock is drastically slowed down due to their near-light speed velocities, extending their perceived lifetime sufficiently for them to complete the journey through the atmosphere. This experimental validation strongly supports the premise that relative motion directly dictates the passage of time, offering a tangible mechanism for one-way travel into the future. This leads directly to the concept of forward time travel, which, under current physical understanding, is not only possible but inevitable, though the practical implications for significant temporal leaps remain technologically daunting. If an astronaut were to embark on a journey aboard a hypothetical spacecraft capable of sustained acceleration to a substantial fraction of the speed of light, say 99.999% of $c, for a period of what felt like 5 Earth years to the astronaut, upon their return, centuries, perhaps millennia, would have elapsed on Earth. The astronaut would have effectively jumped into the distant future. The required energy expenditure, however, scales dramatically with velocity, demanding propulsion systems far exceeding current chemical or even advanced nuclear capabilities, likely requiring breakthroughs in matter-antimatter annihilation or harnessing zero-point energy, technologies that remain firmly on the horizon of engineering feasibility. The second form of time dilation, gravitational time dilation, arises from Einstein's general theory of relativity, which posits that gravity is not a force but a manifestation of the curvature of spacetime caused by the presence of mass and energy. Clocks located deeper within a gravitational potential well, meaning closer to a massive object, tick slower relative to clocks situated in a weaker gravitational field farther away. This effect is also quantifiable, mathematically related to the Schwarzschild metric for non-rotating, spherically symmetric masses. The closer one is to the mass, the greater the curvature, and the slower time proceeds relative to a distant observer. The most extreme example of this gravitational effect is near black holes, regions of spacetime so warped by mass concentration that nothing, not even light, can escape once it crosses the event horizon. Near a black hole's event horizon, time dilation approaches infinity relative to an observer far away. A hypothetical spacecraft orbiting just outside this boundary could spend mere hours completing many orbits, while decades or even eons pass for observers in interstellar space. This concept has been dramatically illustrated, albeit in a highly cinematic context, by the movie Interstellar, where proximity to the supermassive black hole Gargantua resulted in 1 hour elapsed near the water planet being equivalent to 7 years on Earth, a depiction that, while exaggerated for dramatic effect, adheres faithfully to the underlying mathematical framework of general relativity concerning extreme gravitational fields. Even on Earth, this effect is measurable. Atomic clocks placed at the top of a tall skyscraper run infinitesimally faster than identical clocks placed in the basement, a difference so small it was only precisely confirmed in the early 21st century using high-precision optical atomic clocks, further solidifying the understanding that gravity is inextricably linked to the temporal dimension. These established principles of relativity, velocity and gravity both warping time, provide a robust, scientifically validated pathway to the future. Travel to the past, however, introduces layers of complexity, paradoxes, and theoretical hurdles that push physics to its absolute limits, demanding geometries of spacetime that may not be physically realizable or that violate fundamental causality principles. The primary theoretical mechanism proposed for backward time travel involves the creation of closed time-like curves, or CTCs, which are paths in spacetime that return to their starting point in both space and time, essentially allowing an object to interact with its own past. The most frequently discussed, though highly speculative, method for generating CTCs relies on exploiting extreme spacetime curvature, often involving exotic matter or astronomical configurations. One prominent theoretical construct is the traversable wormhole, often called an Einstein-Rosen bridge. A wormhole is a hypothetical tunnel connecting two disparate points in space-time, potentially across vast spatial distances or across different points in time. Mathematically, the equations of general relativity permit the existence of wormholes, but their stability and traversability present immense challenges. A standard, unmanipulated wormhole would collapse instantaneously, faster than even light could pass through it. To prop a wormhole open long enough for passage, making it too traversable, the throat of the wormhole must be stabilized by matter possessing negative mass or, more accurately, exotic matter exhibiting negative energy density. Negative energy density violates the averaged null energy condition, one of the classical energy conditions in general relativity, which posits that the energy density integrated along any null geodesic light ray must be non-negative. While quantum field theory allows for transient, localized violations of this condition, as observed in the Casimir effect, where the presence of uncharged, conducting plates placed very close together in a vacuum results in a measurable attractive force due to the suppression of vacuum fluctuations between the plates, creating a region of lower energy density than the surrounding vacuum, maintaining a macroscopic, stable region of sufficient negative energy density required to hold open a wormhole is currently beyond known physics. Theoretical calculations suggest that the amount of exotic matter needed to stabilize a wormhole large enough for a human might be equivalent to the mass energy of a large planet, albeit negative in sign. If such a traversable wormhole could be engineered, backward time travel becomes conceptually possible by manipulating the time differential between its two mouths. Suppose one mouth of the wormhole is kept stationary on Earth while the other mouth is accelerated to near the speed of light and then brought back, similar to the astronaut scenario discussed earlier. Due to time dilation, the accelerated mouth would have experienced significantly less time than the stationary mouth. If the stationary mouth has aged, say, 10 years, and the traveling mouth has aged only 1 year, entering the stationary mouth and exiting the traveling mouth would result in the traveler arriving 9 years in their own past relative to the departure time of the stationary mouth. This construction is often referred to as a time machine based on the GOT mechanism or generalized time machine solutions derived from general relativity. However, the very possibility of creating CTCs immediately invokes the specter of paradoxes, most famously the grandfather paradox, wherein a traveler goes back in time and prevents their own existence, leading to a logical contradiction. Physicists have proposed several theoretical resolutions to this conundrum, suggesting that the laws of physics might intrinsically forbid such paradoxes. One prominent contender is the Novikov self-consistency principle, proposed by Igor Novikov. This principle suggests that if time travel to the past is possible, the probability of any event occurring that would lead to a paradox is zero. In essence, any actions taken by the time traveler in the past are already incorporated into the history that led to their journey. If you try to prevent your grandfather from meeting your grandmother, some unforeseen event, a sudden illness, a slip, a misremembered address, will inevitably intervene to ensure that the historical timeline remains consistent. The universe, through the constraints of self-consistency, prevents paradoxical actions from ever being completed. This implies a deterministic view of history where free will concerning altering the past is illusory, constrained by the requirement for logical coherence. Another, more radical resolution emerges from the many worlds interpretation of quantum mechanics, often invoked when discussing time travel. In this view, any event that could have multiple outcomes results in the universe splitting into multiple branches, one for each outcome. If a time traveler attempts to alter the past, they do not alter their original past but merely create a divergent branch of reality. When the traveler prevents their grandfather's meeting, they simply transition into a new timeline where they were never born, while their original timeline remains untouched and consistent. This elegantly sidesteps the paradox by multiplying realities rather than violating causality within a single history. Beyond theoretical constructs involving wormholes and exotic matter, other highly speculative mechanisms for time manipulation have been explored. One involves utilizing the immense gravitational field of a rapidly spinning black hole, a Kerr black hole. Solutions to the Einstein field equations for a rotating black hole suggest that spacetime near the singularity is so twisted that it could theoretically allow for paths that loop back on themselves. However, navigating such a region without being torn apart by infinite tidal forces or encountering the singularity itself remains practically impossible, and even if traversable, the resulting pathways might still be constrained by the Novikov principle. Another intriguing, albeit less direct, method involves manipulating the geometric properties of spacetime on a cosmic scale, perhaps using immense cosmic strings, hypothetical one-dimensional topological defects predicted by some theories of particle physics, possessing extreme density and resulting in powerful gravitational lensing effects. Calculations by J. Richard Gott suggests that two parallel, infinitely long cosmic strings moving past each other at near light speed could warp spacetime sufficiently to create a pair of CTCs, allowing for travel into the past between the strings. The primary obstacle here is the sheer cosmic scale required for the setup, the unconfirmed existence of cosmic strings, and the precision needed for the maneuver. The discussion of time travel inevitably forces a confrontation with the fundamental nature of time itself. Is time emergent or fundamental? The block universe theory, often supported by the geometric view of relativity, suggests that past, present, and future all exist simultaneously as fixed points within the four-dimensional block of spacetime. In this view, the sensation of flow is merely a psychological artifact of human consciousness moving along a predetermined path. If the block universe model is accurate, then moving through time, forward or backward, is conceptually akin to moving through space. It is simply a matter of finding the appropriate coordinate transformation, which is precisely what time dilation achieves for forward travel. Past travel, however, requires the coordinate transformation to loop back on itself, requiring the CTCs discussed earlier. Conversely, theories that treat time as fundamentally emergent, perhaps from quantum entanglement or thermodynamic irreversibility, present a less clear picture for manipulating the past. If time's arrow is defined by the inexorable increase of entropy, the second law of thermodynamics, then true reversal of time would require a massive, spontaneous, and highly improbable decrease in the entropy of the entire observable universe, a violation of statistical mechanics on a macroscopic scale. The experience of time flow is strongly correlated with entropy increase. We remember the past, low entropy state, and not the future, higher entropy state. Therefore, to travel backward in time might require the traveler to experience, or cause, a local decrease in entropy so profound that it violates this fundamental cosmic bookkeeping rule. The scientific frontier continues to explore these limits, particularly through quantum gravity research attempting to unify general relativity with quantum mechanics. Theories such as loop quantum gravity or string theory might offer deeper insights into the discrete nature, or lack thereof, of spacetime at the Planck scale, the fundamental unit where our classical understanding breaks down. If time is truly granular, composed of minimum temporal units, traversing these units backward might require a mechanism fundamentally different from those derived from continuous spacetime geometry. Recent advancements in controlling quantum systems have offered tantalizing, albeit limited, glimpses into temporal manipulation at the quantum level. For instance, experiments simulating time reversal in quantum computation, where the evolution of a quantum state is reversed by applying a specific sequence of operations, demonstrate the mathematical possibility of reversing quantum evolution. While this is not macroscopic time travel, it only reverses the specific unitary evolution applied by the researchers. It confirms that the underlying physical laws, at least in the quantum domain, do not inherently forbid temporal reversal under controlled conditions. Furthermore, experiments involving the measurement of time delay in quantum entanglement have occasionally suggested deviations from classical expectations, though interpretation remains fiercely debated. One particularly novel area of research involves exploring the theoretical spacetime geometries near extreme gravitational events, such as the merger of binary black holes, which generate gravitational waves, ripples in spacetime itself. Could the energy and dynamics involved in such cosmic events temporarily create transient, microscopic CTCs that wink out of existence almost instantaneously? Observing or interacting with such ephemeral structures is a monumental challenge, requiring detectors far more sensitive than current gravitational wave observatories like LIGO and Virgo, which currently focus on measuring the spatial distortion of the waves rather than their temporal topology. The philosophical implications of backward time travel, even if physically constrained by self-consistency, are profound, touching upon determinism versus free will. If the future can be visited and the past cannot be changed, what does that imply about the nature of human agency? If we accept the block universe model bolstered by successful time dilation observations, then all moments, from the Big Bang to the eventual heat death of the universe, are equally real coordinates in space-time. Our perception of now is merely our current location along the time axis, much like our perception of here is our current location in space. Considering the sheer scale of the energy and exotic material required for even the most plausible theoretical time machines, the consensus among most mainstream physicists remains that while forward time travel is an established consequence of relativistic motion and gravity, backward time travel, while mathematically allowed by general relativity under highly specific, probably unattainable boundary conditions, remains firmly in the realm of theoretical conjecture, perhaps awaiting a complete theory of quantum gravity to either definitively rule it out based on fundamental principles or reveal a subtle loophole that preserves causality. The quest to understand time, whether by accelerating towards the future or attempting to bend back towards the past, serves as the ultimate testing ground for our understanding of the universe's most fundamental laws, constantly pushing the boundaries of physics from the verifiable reality of orbiting clocks to the speculative necessity of exotic matter in wormhole throats, ensuring that the story of time remains the most compelling narrative in all of science. The bending of space-time, demonstrated daily by the GPS system, offers a concrete foundation upon which the most extraordinary speculations about temporal journeys are built, forever linking motion, gravity, and the inexorable march of moments into a single, malleable reality.